So in this video, I'm going to talk about the definite integral and how to find it not using a graph and not using Riemann sums. And then I'm also going to talk about a really important theorem called the fundamental theorem of calculus. There are no other videos except like within the homework that shows you how to do this. So I was making sure that I cover these concepts. So just as a reminder, when we talk about the definite integral and we write it as the integral and then we put a lower limit and upper limit. So A and B just stand for some number of f of x dx. This is called the definite integral. And what it means graphically, it gives the net area between the x-axis and the function, between these two x values, A and B. Okay, so this means the area under the curve, it's really the area between your curve and the x-axis. So in the previous module, you looked at how to find it graphically, but often we don't have a curve that results in a geometric shape that we know the area formula for. So it doesn't give us a circle or a triangle or a square. It gives us some curve, like if we did x squared, it would look like this. And because it's a curve, I really don't have a area formula. I could try to approximate it using a triangle or Riemann sums, but it's not perfect. So we want like a more specific formula on how to find the definite integral for any function. And that comes into play called a really important theorem in calculus called the fundamental theorem of calculus. And depending on your book, there's like two formulas called the fundamental theorem. So it's either part one or part two, depending on the calculus textbook you read. But how it works is we have to have a continuous function. So suppose our function f is a continuous function on the interval a, b with an antiderivative f. So what that means is that f is the original function, capital F is the original function, lowercase f is the derivative. So capital F prime of x is the same thing as lowercase f. The definite integral from a to b, what we do is we find, if we're given the derivative, so remember this represents the derivative, we find the original function. Okay, so f in this case is the original function. And then what we do is we plug in our upper bound first, then our lower bound, and we subtract them. And that gives us the exact value for this definite integral. So it gives us the exact area under the curve between A and B. So A and B are called the limits of integration. And this formula is called the fundamental theorem of calculus. And the difference between capital F of B and F of A is the net change of the function of F as X varies from A to B. So it's really the change in Y of your original function. Now you could also, like, I feel like this notation is a little bit less confusing, but most textbooks use like the capital F and the lowercase. But if I use the derivative notation instead, what I'm saying is if I'm given the derivative, I find the original function. And then what I'm going to do is I'm going to plug in my upper and lower bound. So how we do it is we find the original function, and usually then we put like a bar here. And then we plug in our upper bound and then subtract our lower bound. So this notation might make a little bit more sense to you. So what we do is we take the antiderivative or the indefinite integral, and then we plug in our upper bound and then our lower bound. Okay, so just to show you like geometrically the interpretation and that they're equal, let's say my original function is 2x. So this is my derivative. Sorry, not my original function. Let my f of x, my derivative, be 2x. And if we take the integral of 2x, we would get x squared, or x squared plus c. I don't know what c is, but I'm going to say, let's say we found that c was 0, so we just got x squared. Or another one we found c is 3. I'm going to show you both and show it doesn't matter what c is. So this is my original function. So what happens is if we take the definite integral from 0 to 2, we know it means the area under the curve. And because 2x is a line, if I'm looking from x equals 0 to x equals 2, well, the shape that results is a triangle. So we would want to find this region. This is the area between the curve and the x-axis, and it's a triangle, and we do know the area formula for a triangle. The area of a triangle is 1/2 base times height. The base in this case is 2. The height is here, this length, which is 4. So I would do, to approximate this integral, I would do 1/2 times 2 times 4. 1/2 times 2 is 1. 1 times 4 is 4. So this definite integral is 4. Now, if I look at the original function, what we said is that this integral is the same thing as capital F of 2 minus f of 0. So it's the same thing as finding the original function and then plugging in my upper bound and my lower bound. So if I check this, either by plugging my numbers into my function or looking at my graph, it doesn't matter either way, you'll get the same answer. F of 2, so when x is 2, y would be 4, because 2 squared is 4. And I would do minus f of 0, well, that y value is 0, or 0 squared is 0, is also 4. And as you see, the area under the derivative between these two x values is the same thing as the change in y. And so what we found, it's the same thing as the length of this line is what f of 2 minus f of 0 represents. Okay, now, what if c is something else? It really doesn't matter what c is. Like, let's look at if c, our constant, was 3. It's going to give me the same thing. Okay, if I found f of 2, here's 2. On my graph, it's here. Well, that y value is 7, or you could plug it in here to find it. 2 squared is 4, plus 3 is 7. F of 0 is this y value, which is 3, or you could find it by doing 0 squared plus 3 is 3, and then 7 minus 3 is 4. So notice it didn't matter that my c was different, I still get the same value because the change in y between these two points is still the same. The constant, all it does is move the parabola either up if it's positive or down if it's negative, so it doesn't change the difference between the two y values. So this is just to show you kind of the geometric application of it, that the area under the derivative is the same as kind of the change in the y of the original function. Okay. So let's do this one. And we'll show how to like apply this formula to problems. And in this case, I am going to put the plus c. We usually don't, and I'll show you why on this problem. But after I do this problem, I won't put the plus c. So when you have a definite integral, the first thing we do is we take the integral of each term like we learned before. So where we add 1 to our exponent, so 3 plus 1 is 4, and divide by my new exponent. Okay, 1/3 is a constant. So the derivative of constant is just that constant times x. And like I said, in this case, I'm going to put plus c just to show you what happens. And I then, when I have a definite integral, which means I have bounds, the notation usually used is we put a bar and then we put the lower bound and the upper bound. So we remember we still have work to do. We need to plug these in. So then we use that fundamental theorem of calculus, which says what we do is we plug in like this is equal to f of 3 minus f of 0. Okay, we're saying this function is f lowercase f or f prime. So we find the antiderivative and then we plug in our upper bound and subtract our lower bound. So I would plug in my 3 first. That's my upper bound. Okay, and I only plug it in for x. I don't plug it in for c. minus, and then I'm going to plug in my lower bound. Now, when you subtract, this has to be in parentheses because you're subtracting this whole quantity. So if we simplify, 3 to the 4th is like 3 times 3 times 3 times 3 is 81. And I'm just going to leave it for now as 81 over 4. 1/3 times 4, this is like 4 over 1. So 1 times 4 is 4. 3 times 1 is 3. Still have plus c. Minus, okay, 0 to the 4th over 4 is 0. 1/3 times 0 is 0. Okay, 0 minus 0 is 0. 0 plus c is just c. Now, notice what happens with the c's. Well, c minus c is 0. They just cancel, and that will always happen. So because of that, when we do definite integrals, because it's just kind of extra work, most of the time we don't put plus c. So usually we just do this and then plug in our 0 and 3. So the big difference is if it's a definite integral, which means they have numbers on the bottom and the top of the integral, you don't have to put plus c because we'll plug in our bounds and then the c's would always end up canceling. Now, if that's going to mess you up or you're not going to be sure when to put it and when not to, you're welcome to put it, but it just gives you more work. And so the last step is I'm going to add the 81 over 4 plus 4/3, and I'm just going to use my calculator instead of getting a common denominator. And generally we like to leave these as fractions so that we don't have to round them. So it's 259 over 12. Let me just show you just in case you don't know how to turn it to a fraction on your calculator. So if you do 81 over 4 plus 4/3 and then hit enter, hit math, and then it says FRAC, which stands for fraction, frac, hit enter and then enter again, and it will give you the fraction. So this value gives me the area under this curve between 0 and 3 for your x values. So I'm going to do a few more examples of the definite integral. Okay, so I want to take the definite integral between 1 and 4 of 5 the square root of x minus 5x. Before I do that, I need the square root to be an exponent. So I'm going to change it to 1/2. And technically there should always be parentheses around this because we're putting the dx with both of them. But a lot of times it's left out and that's fine. So if you don't want to write the parentheses every time, that's okay. So when I take this integral, I'm going to write this out just because of the 1/2. So I would take 1/2 and I would add 1, and then I would divide by that new exponent. This is x to the first. So 1 plus 1 is 2 over 2. I don't need the plus c because it's a definite integral. So instead I write the bar and I put my numbers. That's a reminder that I need to plug it in. Okay, so 1/2 plus 1 gives me 3/2. And 5 over 2 would give a decimal, so I'm going to leave it like that for now. And again, if you're going to do this, you would do 5 divided by and then put your 3/2 in parentheses and then go to math fraction. You don't want to round these, you want it exactly. So this would be 10/3, okay, or you can multiply by the reciprocal if you want to do it by hand. And then I'm going to plug in my upper bound to each term minus, and then I'm going to plug in my lower bound to each term. Now, it's completely up to you. If you want to type this whole thing in your calculator, you can. If you want to do it in pieces, you can. If you're going to do it all at one time, just be really careful when typing it in. I didn't leave the exponent. Don't forget, if you have a calculator like mine, to move out of the exponent when you write your next terms. All right, now if I was going to do this all at one time, I would need the parentheses like I have it here because I didn't distribute the negative. And I got an arrow over to get out of the exponent, and then I would have 5/2 times 1 squared, close my parentheses for this one, and then hit enter. And I'm going to leave my answer again as a fraction, so I'd get -85/6. Or you can do it all like each separately and then add them all together. You should get the same answer. Okay, so we're going to do one more with an e. So it's the integral from 0 to ln of 3 of e to the x minus e to the negative x, and then that whole quantity over 2. Okay. So because I have a dividing both terms by 2, I need to simplify first by dividing everything in the numerator, each term in the numerator by 2 before I take the antiderivative. Okay, so now when I take the antiderivative, okay, e to the x is just itself, and we leave that constant in front. Okay, e to the negative x is itself, again, it would be over 2, but remember, you always divide by the derivative of the exponent. So the derivative of negative x is -1. Okay, so I would need to also divide by -1. So what this gives me is minus e to the negative x over -2. And then to make my life a little bit easier, I have minus, and then this is like a negative. You can put the negative, like the 2 here, is the same thing as making the whole fraction negative, and then minus a negative is just plus. So that's like the final simplified antiderivative, and then I would plug in my upper bound to both minus, and then my lower bound to both. Again, you need parentheses around the lower bound. So whether you remember this or not, or have learned it, I don't know, but if you have e to the ln, they're inverses of each other. So you actually just get whatever number it is, which is 3. So this just becomes 3/2. Now, if there's something in between them, like a negative or any other number, it does not work as well. So you can just type it in your calculator. If you know the log properties and how to do that, then you can do it that way if you want to do it by hand, but this is probably much easier. So just do e to the negative ln of 3 divided by 2, and then hit math fraction to get it as a fraction. So we get 1/6. Okay, and then e to the 0 is the same as anything to the 0, which is just a 1. Again, you can type in your calculator e to the 0 to find it, and you can also do e to the -0, but -0 is the same thing as just 0, so it's still e to the 0, which is 1. So this is also 1/2. 1/2 plus 1/2 is 1. So I'd have 3/2 plus 1/6 minus 1, and I'm not going to get a common denominator, I'm just going to do it in my calculator. So I'd get 3/2 plus 1/6 minus 1, and then again, leave this as a fraction, and I get 2/3. So that's my final answer for my definite integral, or the area under the curve. Okay. So let me know if you have any questions, but that's how you use that fundamental theorem of calculus to find the definite integral.